Hello everyone, I hope you are all doing fine. So this is our first lesson for Calculus 3. The topic is on sequences, specifically infinite sequences. So first, let us define what is an infinite sequence. So an infinite sequence of real numbers is an ordered unending list. So we would denote that by a1, a2, a3, and so on up to an minus 1, an plus 1, and so on. And these are all, of course, numbers. So you would notice here it says ordered because the first term would be our a1, second term is a2, and so on. We have the nth minus 1 term is a of n minus 1, the nth term is an, and the next term to that is an plus 1, and so on. It is unending because, of course, it is infinite, so it goes on forever. However, we would like to know if our sequence is going to if it's just increasing, decreasing, or if it's going to a certain number. So first, let's look at some sequences here. So there are different ways that we can denote a sequence. So we can have this one. We can denote it like this. So there's a brace, and then there's a subscript and a superscript. This would tell us that the first value that we can substitute to n is 1, and it goes on to infinity. We can also write it this way, so an is equal to 1 over n, and here our n would also be substituted. We usually start with 1 and then go on to infinity. Of course, we use only the natural numbers, but sometimes we can use other numbers. We can start with something else. For example, this 1 over 10 to the n, we can start with 0, because if we substitute 0 here, our number would still be defined. And then we can also write it this way, and then we have this. So for this sequence, it would be undefined if we use an n that is less than 3, because if this is 2, then that would be 6 minus 7, which would give us negative 1, and of course square root of negative 1 is an imaginary number. And then we also have here for sine n pi over 2. So we start with 1, go on to infinity, or write it this way. And we can have a sequence like this. So when we substitute the natural numbers to our sequence, 1 over 1, of course, is equal to 1. 1 over 2, 1 half, 1 over 3, 1 over 4, and so on. It goes on to infinity. For the second sequence, we can have 1 over 10 to the n. So 1 over 10 to the power 0. Again, remember, any number raised to 0 is equal to 1. And then 1 over 10 to the power 1, it's simply 1 over 10. 1 over 10 to the power 2. 10 to the power 2 is 100, and so on. And we also get these numbers. So these are the sequences, and these are the formula for those sequences. So again, let's look at the sequence 1 over n. Again, if our n is equal to 1, then 1 over n is just equal to 1. If n is equal to 2, then that's 1 half, or 0.5. If it's equal to 3, then that's 1/3, or 0.33. If n is equal to 10, then that's 0.1. If n is 100, so remember again, what we want to do here is make n go to infinity, meaning we just make it larger and larger without bound. So if it's 10, that's 0.1. If it's 100, 0.01. 1000, 0.001. 10,000, 0.0001. So you will notice here our number is getting smaller, getting very, very, very small. So the question here is, is it going to any number in particular? Before we answer that, let's look at another sequence. So let's say we have the sequence 2n plus 1 over 3n minus 1. So with this, we can start our n at 0, still going to infinity. So if our n is equal to 0, then the number that we get is equal to negative 1. If n is equal to 1, then we get 1.5. If 2, it becomes 1. If it's 3, 0.875. Then we get the 0.724. This is an there are more decimals here, but I just truncated it here. We just used 3 decimal places just to show what's happening. And also I did not round off, I simply truncated so that we would have a better sense of what's going on. If our n is 100, we get 0.672. If it's 1000, 0.667. 10,000, 0.666. 1,000,000, 0.666. Now you would also notice, if you do your own calculation here, if you use an even bigger number here, something bigger than 1 million, you can go to 10 million, 100 million, and so on. You most likely would always be getting 0.666. So this tells us that the sequence is actually going to a certain number, and most likely it is 0.666. However, this is not how we do it in mathematics. We don't just simply put values here. We have to prove, or we have to show, that it really is going to 0.666. Or later on in fraction form, that would be 2/3. Now let's look at other sequences. So we have here the sequence n minus 3. So we can start at 1. If it's 1, then the number we get is negative 2. If it's 2, it's negative 1. If it's 3, it's 0. If it's 10, it's 7. If it's 197, 1997, 10,000, 9,997. So as we make our numbers larger here, as you keep on substituting large n's, you would also keep getting large values of n minus 3. So that tells us that our sequence here just keeps on getting larger. Let's look at another sequence. Let's have the sequence cosine n pi over 2. If our n is 1, cosine of pi over 2, that's 0. If our n is 2, that would be cosine of pi, that's equal to negative 1. If our n is 3, that's cosine of 3 pi over 2, that is again 0. If our n is 4, we would have cosine of 2 pi, that's equal to 1. If it's 5, cosine of 5 pi over 2 is 0. If it's 6, then we would have cosine of 3 pi, which is equal to negative 1. If it's 7, cosine of 7 pi over 2 is 0. If it's 8, then cosine of 4 pi is equal to positive 1. So you will notice here, it seems to just be revolving with these numbers: 0, 1, 0, 0, negative 1, 0, 1, 0, negative 1, 0, 1. So as you keep on putting here values of n, this just keeps on cycling through these numbers. So this tells us that it's actually not really going somewhere, but it cycles through these numbers: 0, negative 1, 0, and 1. Let's look at another sequence. So our sequence here, we have negative 2 raised to the power n. If our n is equal to 1, then it's the value is equal to negative 2. If our n is 2, it's positive 4. If it's 3, it's negative 8. If it's 10, it's positive 1024. If it's 11, then it's negative 2048. So with this, we can't say that it's increasing or decreasing, because you would get positive, then negative, positive, then negative. Remember, if your exponent is odd, then this whole thing is negative. If it's even, then this whole thing is I'm sorry, if it's odd, then this whole thing is negative. If it's even, then this whole thing is positive. So the values keep on changing from negative to positive. The absolute value increases, but the actual value would keep on changing from positive to negative. Okay. So what do you want to learn here? We want to learn if our sequence is converging, that is going to a certain number. So let's have the definition. We say that the sequence an converges to the real number L, or has the limit L, which we write as limit of an is equal to L as n approaches infinity, provided that an can be made as close to L as we please merely by choosing n to be sufficiently large. That is, given any number epsilon greater than 0, there exists an integer n such that the absolute value of the difference of an and L is less than epsilon for all n greater than or equal to n. So if we can find this L is the number that the sequence is going to, as we keep on increasing the number for n, as we keep on increasing the value of n. Now if your sequence is not converging, if it's not convergent, then the sequence is said to be divergent, or it diverges. Now, before we go into the analytical part of finding the convergent number or the limit of a sequence, let's first review some values concerning infinity. When we say infinity, this is not an actual number. This just means that our values keep on increasing without bound. So if we add infinity and infinity, of course that's infinity. So something very, very large plus something very, very large is equal to something very, very large. Infinity plus any number a, this is a constant here. Of course that's infinity. So basically something very large added with something that's not really large would be something very large. Something very large, infinity, subtract that with something that is not so large, that's still something very large. So infinity minus a is equal to infinity. Multiply infinity by a positive number, that's infinity. Infinity multiplied by a negative number is negative infinity. 0 multiplied to infinity is 0. Again, any number multiplied by 0 is equal to 0. Now, any constant, any number, divide that by infinity is equal to 0. So you have something here that's not so large, a certain number, divided by something very, very large, you would get a very, very small number. And remember, this one keeps on increasing without bound. So if it keeps on decreasing without bound, eventually it will go to 0. Now infinity divided by a certain constant is still equal to infinity. Now here is where we need to remember. Infinity minus infinity is indeterminate. We don't know what will happen if we subtract infinity from infinity, because this is a number that increases without bound, is also something that increases without bound. We cannot say that it is 0. Also, if we divide infinity by infinity, that is also indeterminate. So later on, when we do our limits, what we must remember is that we should not be able to get infinity divided by infinity, nor infinity minus infinity. So there is a way that we can avoid getting these situations. Okay, now let's recall your calculus 1. When you have, let's look for an empty space first. Okay, just here. So when we were going to evaluate limits, what we would do, let's say we want to find what is the limit of 3x as x approaches 2. What we simply do is substitute, so that is equal to 3 times 2, which is equal to 6. Now the concept here of our n approaching infinity is actually also quite similar. basically what we would be doing is substituting infinity to the value of n. So in this case, we want to find the limit of 1 over n as n approaches infinity. So this is equal to 1 over infinity. Now remember what we have here, a divided by infinity is equal to 0. So that means the sequence 1 over n converges to 0. Let's go back to that slide. Okay, here, this is the sequence 1 over n. So what was happening here, the number keeps on decreasing, decreasing, and it is approaching to 0. The number here will not become equal to 0, but it is approaching 0. Remember the concept of limits. We are only approaching a certain number. We don't want to see what happens when it becomes that number, only that it approaches that certain number. Okay, let's have our next example. So what is the limit of n minus 3 as n approaches infinity? So this is equal to infinity minus 3, and of course that is still infinity. Okay, so this one, what is the limit of 2n plus 1 all over 3n minus 1 as we approach infinity? Now you might be tempted to do now 2 times infinity plus 1 over 3 times infinity minus 1. So we get infinity plus 1 all over infinity minus 1. Infinity plus 1, that's infinity. Infinity minus 1 is infinity. So you get infinity divided by infinity, and you might say 1. Nope, that is wrong. Remember what we said here? Infinity divided by infinity is indeterminate. So we don't want to do infinity divided by infinity. So how do we find this limit? We will now be using this rule called L'Hopital's rule. It's spelled as hospital, but because this person, Hopital, is French, they pronounce it as Hopital. S is silent. So it says that the limit of the ratio f of x over g of x as x approaches a is equal to the limit of the derivative of f of x over the derivative of g of x as x approaches a. Basically, what it will want us to do is to get the derivative of the numerator over the derivative of the denominator, and maybe that would give us a better way of finding the limit. So let's try doing that. So we go back to the example 2n plus 1 all over 3n minus 1. So applying L'Hopital's rule, remember we are not yet evaluating the limit, so make sure to write still limit as n approaches infinity. Now what is the derivative of 2n plus 1? That is 2. What is the derivative of 3n minus 1? That is 3. The limit of 2/3 as n approaches infinity. Remember calculus 1, the limit of any constant is the constant itself. So the answer here is 2/3. So let's go back to that sequence. Okay, here. So this is 2n plus 1 all over 3n minus 1. So this one, as we keep increasing our n, it becomes 0.66666, never ending decimal. Repeating, non-terminating, or 0.666, we know that this is equal to 2/3. So the sequence, so we say that the sequence 2n plus 1 all over 3n minus 1 approaches 2/3. So this is the limit of, or converges to 2/3. Let's have another example. Let's say we have the sequence 5 minus n squared all over 2n plus 3. So with this, so when do we apply L'Hopital's rule? We will apply L'Hopital's rule until either the numerator or the denominator or both is just a constant. If we still have a variable, we keep on getting the derivative. So we do not stop at first derivative if there is still a variable. So again, we only stop if it's already a constant, then we evaluate the limit. Okay, so this one will be still limit as n approaches infinity of what's the derivative of 5 minus n squared? That's minus 2n. What is the derivative of 2n plus 3? That is 2. Okay, so the denominator now is a constant, so we can now evaluate the limit. So this is equal to negative 2 times infinity all over 2. Of course, negative 2 times infinity, that is negative infinity divided by 2, still negative infinity. So therefore, we say that the sequence 5 minus n squared all over 2n plus 3 diverges. Or you can write is divergent. Let's have another example. So let's say we have the sequence 7 minus 2n plus 4n squared all over 6n cubed plus 7n squared minus 2n minus 3. So with this, we apply L'Hopital's rule. So we get the limit as n approaches infinity. So get the derivative. 7 minus 2n plus 4n squared, 7 becomes 0. Negative 2n becomes minus 2. And then 4n squared becomes plus 8n. Now for the denominator, 6n cubed will become 18n squared plus 14n minus 2. We still have a variable n, we still have variables n, so we apply again L'Hopital's rule. Again, we are not yet evaluating the limit, so we still have to write the limit. Okay, so that's limit as n approaches infinity of, so again, apply the derivative. Negative 2 becomes 0, 8n becomes 8, and then the bottom we have 18n squared, so that becomes 36n plus 14. Okay, so the numerator is now just a constant, so we now evaluate the derivative. We substitute infinity, so we get 8 over 36 times infinity plus 14. So this is equal to 8. This one, 36 times infinity plus 14, that's certainly equal to infinity. So any number divided by infinity, that is equal to 0. So therefore, we say that the sequence 7 minus 2n plus 4n squared all over 6n cubed plus 7n squared minus 2n minus 3. This sequence is convergent and approaches 0. Let's have our last example. So let's say we have this sequence 4n cubed plus 2n squared minus 9n plus 2 all over 5 minus 2n plus 7n squared minus 8n cubed. So we apply L'Hopital's rule. So limit as n approaches infinity of, so get the derivative. 4n cubed will become 12n squared plus 4n minus 9 all over 5 minus 2, sorry, 5 will become 0. So that will become minus 2 plus 14. Sorry, erase that. Plus 14n minus 24n squared. So we still have variables in denominator and numerator. So we apply again L'Hopital's rule. So 12n squared will become 24n plus 4 over 14 minus 48n. So again, apply the L'Hopital's rule because we still have variables in both numerator and denominator. So this will become 24 over negative 48. So again, this is now just constant, so that is 24 over 48, or that's equal to negative 1/2. So therefore, we say that the sequence 12n squared plus, sorry, that's already the derivative. Let's start over. So the sequence 4n cubed plus 2n squared minus 9n plus 2 all over 5 minus 2n plus 7n squared minus 8n cubed. This is convergent and it approaches negative 1 half. So in this lesson, we have learned about sequences, and what we want to do here is to examine if the sequence would approach a certain number. So we can do that first by doing brute force manual calculations, but the better way of doing that is by applying the concept of limits. So expect that that's what you will be answering in your problem set. That will be all for today. Have a great day. Stay safe.